Hello everyone. So our topic for the applied physics project is quantum computing. Now, I know it sounds complicated and you're probably freaking out right now, but it is not a difficult concept to grasp. At least, hopefully, when we're done explaining it in this video. Okay, so let's start with the basics. We all know what electrons and photons are, right? Electrons are subatomic particles that can move freely about the nucleus of an atom. The photon is a fundamental particle of visible light. Both the electron and the photon can undergo quantum processes, such as tunneling and entanglement.
We're going to talk about today quantum computers. So we need to know what transistors are. Transistors are in quantum and classical computers. So what transistors do is transistors essentially allow current to pass. So if a transistor is open, right, current's moving through the transistor, and if a transistor is closed, current cannot move through the transistor. So transistors are vital for computation. If a transistor is working properly, you can do things like add and subtract, and you can build that up to be anything, multiplication and division, which are just recursive forms of addition and subtraction, and then powers and exponents, which are recursive forms of multiplication. So if you can add, you can do any kind of computation for the most part. Computers rely on these transistors. So quantum computers are no different than classical computers in that respect, and that they also have transistors.
So, transistors basically control the flow of electrons within a chip. It's kind of like how a cell membrane regulates what goes in and out of a cell.
So let's talk about quantum entanglement. What makes a quantum computer different from a classical computer? Quantum computers rely on a process called quantum entanglement to make their computations run a lot faster. You see, with a classical computer, you have to use a classical algorithm, which relies on either heuristics or just algorithmic steps. And an algorithmic step would be something like, at this step, add this number to this number, or subtract this number. And that is at its most basic. Some algorithms have things like move this flag somewhere, but that's still just adding the position of the flag. So it doesn't really matter what you're talking about in terms of your algorithm. It always boils down to pretty much simple operations at each step. Whereas a quantum algorithm can actually perform multiple operations per step, because what it can do is that whenever you add a quantized electron, like if you process a quantized electron and say the sum of 0 plus 1, you also simultaneously can process 0 plus 0, 1 plus 1, and 1 plus 0, which 0 plus 1 and 1 plus 0 are equivalent to each other. But if you did subtraction, you'd find that they wouldn't be. So it's actually very useful to be able to process all four forms of that simple operation addition simultaneously. Now, you can actually do a similar thing with very complex operations. And if you build a correct quantum algorithm, you can actually process very complicated computations simultaneously. This is what a quantum prime factoring algorithm does. So these quantum computers, with their entanglement, allow computations to occur more quickly, because if you process a single particle, if it's entangled or within the same quantum system, you can think of it like a sphere, and the particles are in this quantum system, which is represented by this sphere. If one particle moves, the other particle moves with it to try and almost balance the system, is a good way to think of it. Um, so if you wanted to run a computation, you'd compute the first particle, move it, and a second particle would also be computed simultaneously. It would move. So then if you check the positions of both particles, you get two results for one operation.
Now, quantum entanglement is when two particles are linked, and it is through this link that when one particle is changed in any way, the other particle reacts in the same manner. This is done simultaneously and instantaneously. It's similar to a chemical equilibrium system, except that it is now a quantum system. The particles change in accordance with one another in order to maintain the balance of the system.
But the issue is, whenever we start to get transistors to be too small, they start to undergo a thing called quantum tunneling, because quantum tunneling just refers to the probability that a quantum particle will tunnel or move through matter, as opposed to not moving through it from reflecting, essentially. So this graphic should illustrate that process fairly well. So these quantum processes like quantum tunneling are problematic for transistors, because if the particles move through the object like that, what happens is you get an issue where the particle has moved through and the transistor has failed to stop it, even though it was attempting to. That means that your particle has now sent a signal through, so you get a miscalculation. So if that were to happen, if you're trying to add the numbers 2 and 4, for example, you could end up getting a result other than 6, something like perhaps 8 or something smaller like 4, even though you were adding 4. So this signal bleed is really bad because it causes inaccuracies in computers, and that will lead to massive problems if you're doing something that requires a lot of precision.
So for our topic, we decided to talk about two fundamental aspects of quantum computing, tunneling and entanglement. Quantum tunneling is the probability that a particle will pass through an object. Now, the way that these particles pass through objects is similar to the way that a ghost would phase through a wall. This visual representation of quantum tunneling shows that, with this particle sort of phasing through the barrier in front of it as a wave. This is where particle duality comes into play. No matter is actually displaced during tunneling because it is able to move through as a wave rather than a physical particle. The wave passes through the object without changing said object's atomic structure. However, in real life, the chances that a particle can actually tunnel through an object is very low. The chances of this increase as the object gets thinner all the way to an atomic level.
So we mentioned Moore's approximation in our paper. Moore's approximation refers to the fact that computer parts change in size as time passes. The part shrinks to about half its original size, roughly every 2 years. This means that the amount of transistors in the chip doubles. But since the part is continually shrinking, this means that the probability that a particle will tunnel through it increases. Eventually, the computer part will become so small that tunneling will become a frequent occurrence.
Classical computers have to use classical algorithms, which rely on heuristics or algorithmic steps. An algorithmic step would be an instruction like, at this step, add this number, subtract this number. Some algorithms may seem more complicated, such as the quicksort algorithm that causes flags to move among a set of numbers. These flags are just list positions, which are incremented. This goes back to addition. All classical algorithms are like this, where every step boils down to a simple operation. However, a quantum algorithm can perform multiple operations per step. This is possible because when a quantized electron is processed, its entangled electrons are also processed, so multiple operations can be performed simultaneously. Recently, NASA and Google partnered to buy D-Wave, a quantum computer. Google wanted to use this to improve their search engine algorithms, but it's still mostly used by NASA. NASA currently uses it to try and categorize and analyze a lot of potentially habitable exoplanets. Obviously, quantum computing is very important and relevant today, and hopefully we've made it easier for you to understand. This concludes an explanation of our topic. Thank you.